We present DecentNeRF, the first decentralized approach using neural radiance fields that can learn immersive views of millions of scenes worldwide from crowdsourced images. Our innovative framework harnesses the power of geotagged images collected from countless scenes across the world. These images often remain untapped within users' personal camera rolls. As you can see, different users have captured unique viewpoints of a given scene. DecentNeRF learns photorealistic scene representations from these diverse perspectives without requiring users to share their actual images with a central server. This decentralized approach uses several orders of magnitude less server computation compared to a centralized solution, hence making it a scalable solution. But before we dive deeper, let's talk about why we would want to learn NeRFs from geotagged images. Learning NeRFs from geotagged images is an important and unsolved problem. For instance, we can significantly enhance the Google Maps immersive view experience for streets and indoor spaces by leveraging the personal images captured by users themselves. Another example could be live events. Imagine being able to virtually experience a live event that users have recorded, rendering them for vivid, immersive viewing long after the concert. Furthermore, geotagged images of various spaces within a city can be harnessed to create detailed 3D representations, providing valuable insights for urban planning and development. While all these cases are potential applications for the work, in our paper, we focus on the immense potential of decentralized NeRFs for virtual phototourism. Creating NeRF from crowdsourced images presents two significant challenges. First, crowdsourced images may contain personal content that users are hesitant to share publicly. As you can see in this user image, captured on a personal device, it features both scene-specific global content, such as the monument, and user-specific personal content, like the individual captured in the frame. Secondly, learning NeRFs from millions of scenes in a centralized fashion is computationally intractable. As we know, training a NeRF for a single scene requires around 100 teraflops of computing power. Performing these computations centrally would not scale for millions of scenes across the globe. This is where a decentralized approach, DecentNeRFs, comes into play. It can create photorealistic renderings, as shown in this video, without requiring users to share their personal data with the server. Furthermore, DecentNeRF demands 4 orders of magnitude less server compute per scene, making our solution scalable for learning NeRFs at a global scale. DecentNeRF employs a 3-step approach drawing concepts from NeRFs, federated learning, and secure multi-party computations to address the challenge of creating NeRF from crowdsourced images. First, we model the multi-view visual data as a combination of the global MLP for the 3D scene of interest and a personal MLP for the user's personal information. We propose a federated learning procedure to learn the global Radiance field by aggregating global MLPs from users. Note that the heavy NeRF training costs are now distributed to the users. Next, unlike typical federated learning, where each user's contribution is weighted equally in the average, we introduce a novel federation procedure. Here, the per-user scaling is learned implicitly to maximize visual fidelity. Lastly, to prevent the server from accessing individual users' global Radiance fields, we employ a secure multi-party computational protocol for aggregation. This secure aggregation minimizes the reconstruction of personal content by the server compared to existing approaches. By integrating these 3 concepts, NeRFs, federated learning, and secure multi-party computation, DecentNeRF offers a robust and scalable solution for creating photorealistic NeRF representations from crowdsourced images while addressing privacy concerns and computational challenges. Our results demonstrate that DecentNeRF can learn photorealistic renderings of scenes from the phototourism dataset with 10,000 times less server compute than our centralized approach. The reconstruction quality of the global content is on par with the centralized baselines like NeRF in the wild, and significantly better than a naive, decentralized approach such as federated NeRF. Notably, compared to other approaches, our reconstructions do not exhibit blobs or artifact in places where personal content was originally present in the source images. This is a crucial advantage, as it ensures that the rendered scenes maintain a natural and seamless appearance without any disruptions or distortions caused by the presence of undesired personal information. Apart from the decentralization benefit of low server compute, our results and analysis also demonstrate that DecentNeRF minimizes the rendering of personal content by the server. In a centralized approach like NeRF in the wild, users would have to share their personal images directly with the server. While a naive decentralized approach like FedNeRF attempts to address this issue by having users share individual global MLPs with the server, we demonstrate that these MLPs still contained personal content. DecentNeRF, on the other hand, employs secure aggregation to ensure that the server only accesses the aggregate global MLPs, which we demonstrate to contain minimal personal content. We also show a quantitative analysis using an off-the-shelf person detection network that we run on our training images. Persons are a part of personal context, and we show that the network failed to detect people using our approach versus existing approaches. This quantitative analysis further reinforced the effectiveness of DecentNeRF in minimizing the reconstruction of undesired personal content by the server. In this slide, now we showcase the ability of DecentNeRF to separate global and personal content effectively. Initially, we observed that the personal content is present in the user's global MLPs. However, over multiple rounds of federation, our 2-MLP approach gradually shifts the personal content over the user's personal MLPs. This separation process results in a significant improvement in reconstruction quality at the server. As the personal content is progressively isolated from the global scene representation, the server's rendering becomes increasingly accurate and faithful to the true global content. Finally, we showcase one of the key features of DecentNeRF, our novel learned federation approach for weighing user contributions to the server global model. We observe that user images can have varying levels of personal content, which manifests as varying degrees of occlusion. In this example, the first 4 users have high occlusion, while the next 4 have low occlusion. Our learned federation algorithm, initialized with weighing users' contributions equally for multiple federation rounds, starts implicitly weighing users with less occlusion more heavily. We compare the reconstruction quality of our learned federation approach with that of FedNeRF, and an ablation of DecentNeRF without the novel learned federation. Our learned federation learns to weigh users with less occlusion more heavily, boosting the PSNR on global content. This learned federation approach is a significant advantage of DecentNeRF, as it can adaptively weigh the contributions of each client explicitly, without relying on predefined heuristics. This dynamic weighing process ensures that the global scene representation benefits from the most informative user contributions, leading to overall improved reconstruction quality and visual fidelity. We have more details in the paper. In summary, we present DecentNeRF, the first decentralized approach using neural radiance fields that can learn immersive views of millions of scenes worldwide from crowdsourced images. We show our approach addresses key challenges in learning neural fields from crowdsourced imagery by sharing minimal personal content while using 10,000 times less compute than centralized techniques. Please refer to the paper for more details.